Good day again, everybody. Today we look at projectile motion, worked examples. In our first example, an arrow is shot horizontally with a speed of 60 meters per second at the top of a cliff 120 meters high. In both instances, and these two examples, please remember, draw a diagram. The first question is, how long will it take the arrow to strike the ground below? Now, an important point to remember is that our vertical distance is, of course, 120 meters. And that is given by our equation of motion symbol, S. Also, 60 meters per second represents the horizontal component of velocity, in this case speed. The range is the total horizontal distance covered and is normally denoted by capital R or XH. Now, let's make a shopping list. What is a shopping list? Well, a list of the quantities that are given in the question or can be deduced by the information quantitatively given. In this case, we resolve vertically and horizontally our vector quantities of displacement, velocity, and acceleration. Since the object is projected horizontally with a horizontal initial velocity, well, our vertical initial velocity is 0. While our horizontal initial component of velocity is 60 meters per second, and since the horizontal component of velocity remains unchanged for a projectile motion, as mentioned in the last video, the final horizontal component of velocity is also given as 60 meters per second. Well, because it is not affected by gravity. Also, the vertical component of final velocity is something that needs to be found. As mentioned, our vertical distance is 120 meters, whereas our horizontal distance or range needs to be found as well. Our vertical component of acceleration is known as the acceleration due to gravity, g. Of course, we can include that moving in the same direction as gravity, we can use positive, and opposing to that would be negative. Our horizontal component of acceleration is 0, as mentioned in the last video, since the change in horizontal velocity is actually 0. Time, t, is the same both horizontally and vertically. What does that mean? The same time it takes to cover the horizontal distance equals the same time it takes to cover the vertical distance. So we begin by resolving vertically by using, of course, S equals ut plus a half at squared. This equation of motion has our vertical distance as 120 meters, our vertical component of initial velocity, and of course our vertical component of acceleration, which is the acceleration due to gravity, g. Now, an important point to remember is that the initial vertical component of velocity is equal to 0, which gives us an equation which is a 120 equals a half 9.8 acceleration due to gravity by t squared. Making t the subject of the formula, our time equals 4.95 seconds. Part B of the question asks us to find how far from the base of the cliff will the object strike or the arrow strike. This is in fact our range, which is our horizontal component of velocity multiplied by our time. Our horizontal component of velocity remains unchanged, which is 60, by time, which we just found, 4.95. Part C asks for the velocity when the object strikes the ground. It is important to remember that this velocity is actually a resultant of both the horizontal component of final velocity and the vertical component of that final velocity. Which do we have? Well, we are given the horizontal component of velocity, which remains constant, as 60 meters per second. But do we have that vertical component of velocity? No, we don't. So we can use vectors, a parallelogram of vectors to be more specific. And in doing so, we can see that there's a right angle between our two components, our horizontal and our vertical components of velocity, thereby giving a parallelogram of forces, which we can then simplify into two right angle triangles. Our vertical component of velocity can actually be found using our acceleration vertically, which is of course g, and our time given. So, what formula do we use? By making velocity the subject of the formula from our equation of acceleration, which is velocity over time, well, we get our vertical component of velocity by saying our vertical component of acceleration is multiplied by time. So, what do we do with both vertical and horizontal components of final velocity? Well, using our triangle, we find our resultant velocity, or the velocity at which the object hits the ground, by using Pythagoras' theorem. Why do we use Pythagoras' theorem? Well, we get a right-angle triangle from our parallelogram of vectors, and by using Pythagoras' theorem, we are able to effectively find that vertical component of velocity and its horizontal component as well to find our resultant velocity. But we're not done as yet. We also need, in always resolving vectors, to find an angle that vector makes with one of the components. Normally, we say the horizontal component. In our diagram, our theta can therefore be found by using the trigonometric ratios, sine, cos, or tan, in this particular case because we have all values in our right angle triangle. In this example, I use tan. Tan being our vertical component of velocity, our opposite side, divided by our horizontal component of velocity, our adjacent side. We therefore get our angle by finding the tan inverse of that value. So how do we state our final answer? The velocity at which the object or arrow hits the ground will be a resultant velocity of 77.2 meters per second at an angle of 39 degrees to the horizontal surface. In our second example, a cannonball is fired at the speed of 40 meters per second at an angle of 45 degrees to the ground at horizontal surface. In the first part, we are asked to find the time it takes for the cannonball to reach its maximum height. As always, a diagram is drawn. Now, since air resistance is ignored or is negligible, well, we have to consider that the time it takes for the object to travel from its starting position to its maximum height equals the time it takes for that object to travel from its maximum height to the same starting horizontal surface. This initial velocity represents a tangent at a point, forming an angle, of course, to the horizontal of 45 degrees. And it represents a resultant vector 40 meters per second, which is made up of a horizontal and a vertical initial component of that velocity. Our maximum height allows the object's trajectory to be symmetric. Once again, in completing a parallelogram of vectors, we find our horizontal and vertical components of initial velocity. For more information on how to do this, please see our videos on vector resolution and resolution of vectors worked examples. In applying trigonometry, once again, we get an equation for the initial vertical component of velocity and the initial horizontal component of velocity. It is also important to note that at maximum height, our velocity is actually zero, because at that instant in time, the object is not moving. Since the initial vertical component of velocity can be found by 40 sine 45 degrees, our vertical final velocity at maximum height, of course, equals 0. Therefore, our time, which we need to find, can be our unknown in our equation. Well, acceleration, which is our vertical component of acceleration, it's minus g. Of course, this is if we take going against the pull of gravity to be negative. So using our equation of motion, our first equation of motion, v equals u plus at, where all components are vertical, or vector components that is, we can therefore make t the subject of the formula. It is important to note that this time of 2.88 seconds is not the entire time for the journey. Instead, it is a time for the object from its starting point, in moving from its starting point to its maximum height. only. Our maximum height, which we denoted as s in our equation of motion, can be found by using s equals ut plus a half at squared. Now, the vertical component of initial velocity at maximum height can be used as 40 sine 45 degrees. Our time we just found is 2.88 seconds can now be used. And please remember that a half at squared means that t, our value for time, is squared, not the entire equation. We therefore get 40.8 meters, approximately. Part C of our question, we were asked to find the time of flight. Now, the time of flight is the time it takes for the object to leave a point and return to that same horizontal surface. And that is 2 times the time that we found, which was the time to move from its starting point to maximum height. This value will end up being 2 multiplied by 2.88 seconds, the time that the object is actually in the air. This value therefore will be 5.76 seconds. And finally, part D of our question. Find the total horizontal distance covered by the cannonball. This is our range, and our range can always be found by using our equation for horizontal velocity, or velocity, where by making xh the subject of the formula, we get our horizontal final velocity multiplied by time. Time, of course, here being our time of flight. And it is also important to remember that the horizontal component of velocity is given as v cos 45 degrees. Now let's look at a simple simulation describing what we just obtained in number 2 of our questions. The object is projected at a speed of 40 meters per second to the horizontal, at an angle of 45 degrees to the horizontal as well. Well, the time we just found was 5.77 seconds. Our time taken to reach maximum height was approximately 2.9 meters per second as shown. And of course, our range was found to be 163 meters. The simulation used was taken from physicsclassroom.com.